Okay, so this is 7-8, the factoring special cases. And just know that you can still use the other method that we learned in 7-7 of the X method to actually solve these, but just you'll start noticing, so you don't have to do it this way. You could still, it'll still work the other way to where you're replacing the middle term. You just have to think what the middle term is. Well, that's 0. So I'll explain this a little bit better. So when it says factor perfect squares, we first have to remember what a perfect square is. Now, one thing I've realized, my LVS students, I don't recall, because I'm doing this with my Math 8 students right now, I don't know if I gave you this sheet, you guys, to where it has perfect squares and then square roots. Oh, that's the second page. And then it had like perfect cubes. I don't know where it is. But anyway, if I did not, I apologize. And anyway, this year's a little different. So perfect squares are like 1, 4, 9, 16, 25. The reason they're called perfect squares is because if you had, you don't have to write this down, but just understand, if you had factors of 16, like 1 and 16, 2 and 8, 4 and 4, well, the 4 times 4 can make a square. This is why these numbers are called perfect squares, because when you make an array of the factors, you can make a square. The number 8. The number 8 only has 1 and 8, 2 and 4. Well, if you made an array of those, you can only make rectangles. You can't make squares. So 8 is not a perfect square. So these numbers are perfect squares, which means they have a whole number times itself that gives you that number. Square root, it's undoing squaring. It's the opposite of squaring. So square root of 49, well, that'll be 7. Square root of 121, that'll be 11. So that's what we're talking about, perfect squares. Is there a whole number times itself that gives you this number? Yes, there is. Okay, so perfect squares. When we factor perfect squares, it's simple if you follow a few things. First of all, it has to be a binomial. It has to be a 2-term polynomial. It can't be a 3-term. That's not going to be what we call factor perfect squares. Both terms are perfect squares. Okay, both terms are perfect squares. And there is a negative sign, a subtraction sign. Okay, so a negative sign between the two terms. So these are some really key in perfect squares, and we call this the difference of perfect squares. So this is what we call the difference of two squares. Now, how do you factor? We first check to see if there's a GCF. There might be a GCF, like down here, we can take out a GCF. So always look for a GCF to make it a little easier. Now, then you're going to take the square root. So this is your square root of the first term to find A, okay, whatever your A term is. Then you take the square root of the second term to find your B, and then plug into the formula. Now A plus B, and then A minus B. This is going to make more sense when you see examples. I don't know why this is sorry. Okay, so for example, we have 25x squared. Well, 25 is a perfect square. X squared will be a perfect squared, and 49 is a perfect squared, and it has a negative. Okay, so this is the difference of perfect squares, which means the square root of 25x squared. The square root of 25x squared. Well, square root of 25 is 5. Now, square root of x squared, we've never done that before. But if you square something and then square root it, you go right back to what you have. So this is 5x. Then the square root of 49 is 7. So you are going to have 5x minus 7, maybe 5x plus 7, 5x minus 7. The order really doesn't matter, but a lot of times I put the plus first. Now, what happens is when you FOIL this, you will lose the middle term. It'll subtract out. It's the exact same thing, except for one has to be positive and one has to be negative. Okay, so that's what we call the difference of perfect squares. So we're going to look at, I know I talked fast, you guys, just pause. Look at these, and we're going to circle the expressions that are difference of perfect squares, as long as they follow these three things. So, okay, x squared, there's like a 1 in front of there. So treat that, yes, that is a perfect square. 81 is a perfect square, and it's subtraction. So this would be a difference of perfect squares. 16 and 36. Well, 16 squared is, square root of 16 is 4. That's x squared. So that's good. And 36, yes, that's a difference of perfect squares. Now this is like a 1x squared, 49, but that's not subtraction. So don't circle that one. That's a trinomial, can't circle that one. This one, nope, not a difference, even though they're perfect squares, not a difference. This one, x squared minus 1, yes, because 1 is a perfect square. The square root of 1 is 1, so that would be 1. 9, x squared minus 4, that would be 1. Those are both perfect squares. 49 and 25, yes, those are both perfect squares. 144 and 1. Now, if you're not for sure if they're perfect squares, just take your calculator. The square root sign on these calculators, it's going to be above your x squared. So shift square root 196. Yep, that is a perfect square. If it comes out to a decimal, it's not a perfect square. Okay, so that is 6425 x squared and y squared. Yes. Now let's say that was y cubed, or like cubed, which you guys really won't see right now, but that wouldn't be. Okay, now GCF. 20 is not, but I would pull out the 20 and see what we get. X squared minus 5. No. So that is not. I would factor out the GCF just to see if it would, because 20 is not a perfect square. 100 is, but when we factor it out, it doesn't work. Okay, now 25x squared and negative 64. Yes. So we're going to factor each of the different squares. If it cannot be factored, write prime. So we're going to look at it. Notice we can take the square root of a squared, and it's a difference, that's good, and the square root of 4. So we're going to have a, and if you want to do minus first, that's fine. Square root of 4 is 2, so you're going to have a minus 2, a plus 2. Okay. Then square root of 81, that's 9, so that's a difference. So this is going to be 9 minus x and 9 plus x. Now if you want to rewrite it to where you have a negative x plus 9, that's fine. But don't make the 9 negative. That's not, it's going to be negative. Okay, now this is not. This is prime. Okay, because it's not a difference. It's a difference of perfect squares. So once you start seeing these, you can do these fairly quickly. You just square root both of these. Square root, square root. So you have 3b minus 10, 3b plus 10. So anytime they're exactly the same but they have different signs, it's going to cut out that middle term. All right, 4h squared negative 25. What is that, a g squared? Yep. So that's going to be, so square root both of those, 2h minus 5g, 2h plus 5g. Okay. Now, square root. So when you're doing the square root of x squared, like I said, when you square, these cancel. It's like saying you do 5 squared and then the square root. Well, square root of 25, because 5 squared is 25, square root of 25 is 5. So what happens is the square root cancels the squaring. Okay, they cancel. Y minus 1, xy plus 1. Maybe it's just my contacts that are blurry. It looks blurry. Okay. So just square root. These are perfect squares, and this is subtraction. That one was not. That's why it's prime. Now let's look at the GCF first, then factor. So right now they're not perfect squares, but if we pull out a 2 on each, look what we get. We get the difference of perfect squares. So really this is going to be 2 n minus 6 n plus 6. Factor out the GCF first, and then it becomes a perfect square. Okay, now 45 and 20. Oh, and also look. Oh, wait. Q. There's a Q cubed, Q cubed, and a Q. So we're going to actually pull out a 5Q, because there's Q's in each. So this is going to be 9Q squared minus 4. So that means we can then factor. These are now perfect squares. So we have 5Q, 3Q minus 2 times 3Q plus 2. Now you have to keep your 5Q there. Don't drop that, because then that whole thing will come up to this term. Okay, we can factor out an M and an N. Now this is just like dividing polynomials, though you did a couple units ago. So you have M squared, that's it. minus 1. M, N, M minus 1, M plus 1. I don't know why I was writing 2. M plus 1. Okay? So what it is, it's just like, anyway, it's doing the difference of perfect squares. Okay, I'm going to do a second video for this on here because I won't be able to finish this in time.